Welcome everybody to the final in our fall series of Quantum Thursdays. And so today we are very pleased to have Layla Hormozi, who is a scientist and group lead of quantum computing at Brookhaven National Laboratory. And today Layla will be speaking to us about topological quantum compiling and introduction. And just as a reminder, if you could just, keep yourself on mute, but if you have any questions, please feel free to put them in the chat, and then we will answer them throughout the session today. Thank you very much. And Layla, thank you and welcome for doing a Quantum Thursday, and I'll turn it over to you to take us through your talk.
Thank you very much, Diana. Thank you for the invitation. So I'll be talking about topological quantum compiling. It's going to be mostly introductory stuff, but I'm sorry, let me just some echoing here. All right, so it's going to be a lot of introductory stuff, introducing you to the idea of topological quantum computing and compiling, and then towards the end I'll basically tell you a little bit about a work that I did in this direction. So and as Diana said, please feel free to stop, unmute yourself and ask me questions along the way. All right, here's the outline of the talk. So I'll start by the basic criteria for reminding you of the basic criteria for quantum computing. Then I will tell you briefly about topological phases, which are basically the substance where this topological quantum computing basically takes place, and in particular fractional quantum Hall states, which are still which remain to be the main representative of topological phases that has been actually experimentally observed. Then I will tell you what I mean by topological quantum compiling. And in the end, I will basically show you a sort of a method for doing topological quantum computing with this particular class of topological phases that are known as Reiter-Zaï states. All right, so let's dive into it. As I mentioned, let's start with what is known as the DiVincenzo criteria for physical implementation of a quantum computer. So if you basically want to build a quantum computer, what kind of physical systems can support that? What are the properties of physical systems that basically can be used as a quantum computer? In these quantum systems, we should be able to define a scalable array of qubits. So we need to have two-level quantum systems, and they need to be scalable. So as you know, for example, the spin of an electron can be the sort of spin 1/2 can be considered as up or down, can be used as logical 0 or 1 for our qubit states. Then we need to be able to initialize these qubits into some simple state. For example, polarizing all the qubits in one direction, initializing our state into all zeros, for example. Then these quantum states need to have long enough decoherence times that we can actually carry out the computation before they lose their coherence. And we need to be able to carry out a universal set of quantum gates, specifically if you're basically focusing on the gate-based implementation of quantum computers, that is. And the universal set of quantum gates, again, consists of all possible single qubit gates, basically all SU2 unitary matrices, and at least one entangling 2-qubit gate, for example, the controlled NOT gate. And finally, we need to be able to carry out single qubit measurements at the end of the process, at least, to be able to read off the results of our computation. So, the main difficulties on the way to build a quantum computer so far have been the existence of errors. And these errors come in the form of systematic errors, and also which are basically built into the system, which come from imperfections of the physical system that lead to. Sorry, is there a question? Okay. So imperfect implementation of the gates or decoherence of quantum states, which happens naturally, eventually, depending on the level of protection that our qubits have and the level of noise that is in the system. So and so and this noise basically affects these categories 3 and 4, the decoherence of qubits, obviously, and the quality of the gates that we are actually applying to our system. So let's dive a bit deeper into this issue of errors. Again, the kind of errors that we talk about here are basically decoherence of qubits, which are random in a sense that they occur due to interactions with the noise in the system. We can't really control it other than generically trying to reduce the level of noise in the system. How much error we get, and we normally cannot control. So these are random errors. And also imperfect implementation of the gates. And these are basically two kinds. One is systematic, and that basically comes from the fact that any physical system that you choose, the operations that you could do on this system are basically limited by the properties of that physical system. So if you actually want to build all SU2 rotations, you have to make approximations based on the physical resources that you have. So some level of approximation, depending on what gate you want to make, is inevitable. So these systematic errors are going to be part of basically any physical implementation of the quantum computer. But in addition to that, even if you manage to sort of build some of the gates perfectly, given the specifics of your quantum system, there's still random noise in the system. There are basically, the actual implementation of the gate is not going to be perfect. So to still introduce some additional random noise to your system as well. And so what are so these are actually sort of big problems. We know that quantum systems are very fragile, and decoherence and sort of interactions with the environment are basically always sort of a big problem. How do we get around them? There are basically two different approaches to this. Most famously, there are these codes that are known as quantum error correcting codes, which were first introduced by Peter Shor back in '95, and then basically was expanded and built on quickly after that. And the basic idea of quantum error correcting codes is that you basically you take your quantum information and then spread it over the global state of many entangled qubits in the system. So other than so in a sense, you basically encode your logical qubits using many physical qubits, many sort of actual physical qubits, and by doing so, local interactions with the environment are not going to affect this quantum information that is basically spread along entangled qubits across the system. A comparable approach, but a different one, was basically pioneered by Kitaev back in '97, and also, which is basically the basic idea behind topological quantum computation. There, the idea is that instead of spreading the quantum information over the entangled state of many imperfect qubits, we basically build near perfect qubits by storing the quantum information into topological states or global states topological degrees of freedom of certain states of matter that are highly entangled, and they're known as topological phases of matter. So in a sense, the first approach, you can sort of think of it as a softer approach. We have these faulty generic qubits, and then we design a code to in effect encode our the quantum information into the state of many faulty qubits, whereas in the second approach, which is more like a hardware approach, you're basically using the inherent entanglement in these topological phases of matter and store your quantum information there. And by doing so, your system is going to be basically, your qubits are going to be inherently protected from the environment. So this is obviously, as the title of the talk suggests, this is the approach that we're going to be talking about today. And so to understand this better, we inevitably have to talk a bit about these 2D topological phases of matter. So the most famous example of these topological states are fractional quantum Hall states. So the setting of this fractional quantum Hall effect is as follows. You have a two-dimensional gas of electrons. Usually how it is done experimentally is that you basically trap a bunch of electrons between two layers of a heterostructure. It's usually, I mean, one of the sort of famous example is gallium and gallium arsenide and gallium arsenide and aluminum gallium arsenide. So you have basically these two layers on top of each other, and then in the middle you can basically trap these gas of electrons. And then you cool your temperatures very low, the level of millikelvin, and then you apply a very high magnetic field perpendicular to this two-dimensional system, usually at the level of several Teslas. Now, when the magnetic field is at certain values of the magnetic field, specifically at those values of the magnetic field that the ratio of the number of electrons to the number of flux quanta is a rational fraction, then these gas of electrons form an incompressible quantum fluid. And this quantum fluid has very interesting properties that has been actually studied theoretically for a long time and extensively. To just give you an example, just as a theoretical curiosity, it's been shown that if you take this two-dimensional gas of electrons and then wrap it around a surface with non-trivial topology, then the ground state of this system is going to be degenerate, and then the degeneracy relates directly to the topology of the surface the system is defined on. So for example, if you basically get this two-dimensional gas that you had and then wrap it around the surface of a sphere, then for this particular state, this particular Phelan fraction, 1/3, then the degeneracy of this system is going to be 1. So it's basically non-degenerate. Whereas if you wrap it around the surface of a torus, then the degeneracy is 3. And likewise, if you sort of keep adding holes to the system, then the degeneracy of the ground state basically grows exponentially with the number of holes in your system. So this is basically a basic property of the ground state of these systems. And its dependence on where they're defined. Now, if these states are basically fairly stable, and if you actually introduce some sort of perturbation to your system, for example, an extra flux quantum or an extra electron, then effectively this extra electron breaks apart in this once it basically enters this quantum fluid, and these quasiparticles, so-called quasiparticles, carry a fraction of the charge of an electron, and more interestingly, they also have fractional statistics, which I will get into later. Now, there is a particularly exotic version of these fractional quantum Hall states known as non-Abelian fractional quantum Hall states, and they have this property that if you introduce a bunch of these excitations, these quasiparticle excitations, to a system that is defined on a trivial surface, for example, a disk, as I'm showing here, then again, the corresponding Hilbert space is going to be degenerate, and its degeneracy grows exponentially with the number of particles, quasiparticles that you have on your surface. Furthermore, states in this these degenerate states within the Hilbert space have this property that they are basically cannot be distinguished from each other by any kind of local measurements. So any kind of measurement that you do to any of these quasiparticles individually or to a small region of this surface, including a small number of these quasiparticles, then you still cannot distinguish between these different states. Only global measurements that basically take into account that the properties of all of these particles can distinguish these different states from each other. So, and then this distinguishing different states within this degenerate Hilbert space can also be interpreted as interactions with the environment. So the way a quantum state decoheres, it basically interacts with the environment. Environment effectively measures that state, and then instead of having a superposition of many quantum states, you basically collapse into a single classical state. So, so the fact that we cannot distinguish these states from each other by local measurements is equivalent to saying that these states are very robust. Local interactions with the environment cannot easily let these states to decohere. So if we manage to basically build these systems with these quasi-particles on them, we effectively have a Hilbert space that grows exponentially with the number of quasi-particles present on it. And in addition, the states in this system cannot be, are pretty robust. They cannot be distinguished from each other by just, local noise or interactions with the environment. So in a sense, it's a perfect place to hide quantum information. It's a perfect memory. It's a great place to actually, you have basically a lot of space to store your quantum information, and then it's going to be protected from the environment. But how about if we actually want to, other than a memory is great, a perfect memory is great, but what if we actually want to do what kind of actual computation we can do on these states? So to understand that, let me just remind you of the statistics of identical particles in 2 dimensions. So if we have, so imagine I have a number of these quasi-particles in 2 space dimensions, and I show time in the 3rd dimension. Now, if I start moving these particles around each other in 2 dimensions, the corresponding word lines sweep out braids in this 2 + 1 dimensional space-time. And note that there's a difference between this pattern of braiding if I exchange my particles in a clockwise manner versus a counterclockwise manner. So these 2 braiding patterns on the left and right are distinct from each other in the sense that there is not a way, there's not a way that I can smoothly move one of these. If I imagine that these, the ends are sort of stuck to the top and bottom surfaces, then there's not a way that I can actually smoothly deform one of them and go from left to right. So I can basically show this operation of braiding on the left, for example, with sigma, and on the right with sigma inverse. And so you can see that sigma and sigma inverse are not the same thing. Now, now just imagine that I do these braids one after each other. So I basically exchange my particles twice. So what I'm doing here is just basically I'm having, say, the first one going around the right one complete around for like 360 degrees. So this operation corresponding to these 2 braids is sigma inverse. Now on the right side, imagine I exchange the first 2 once. So I bring one of them around the other one for 180 degrees, but then I bring it back like so. So in both of these pictures on left and right, the particle that say on the right hand side, the particle that starts on right basically ends up on right. And same here. But you can see that there's a clear difference between the braiding pattern on this side and on the right hand side. Most obviously, on the right hand side, you can see that I can easily basically modify this pattern and just basically take these strings and then pull one on top of the other one and end up in this picture. And this is equivalent to basically doing nothing, letting the 2 particles stay in their space and just not move. Sorry, I'm gonna mute myself for a second because I have to cough.
And just as Layla is taking a moment there, just a reminder to feel free to put any questions you have in the chat function, or feel free to unmute yourself and ask directly.
Right, exactly. Sorry. So, by sort of here, I guess what I wanted to show you is that, exchanging two particles twice just by bringing one particle back where it started doesn't necessarily take me to this state of basically doing nothing. These two are completely different from each other. So, in other words, sigma squared is not equivalent to identity. Now,
Actually, Layla, if you wouldn't mind, we do have a question here.
Sure, go ahead.
From Kade Sheng, is braiding a purely theoretical concept, or is there a proposed experimental scheme for braiding?
Oh, yes, of course there's a experimental way to do that. It's just basically, the thing is that this picture is imaginary, but what we're basically talking about is that, you have basically two particles in two dimensions, and then you move one of them around another one. So when you do that one around another one, then when you consider space-time, braid is basically what is happening. So now you may ask, is there actually a way to do the braiding? Like if you're asking about how you're doing the braiding, there are basically different proposals to how to do that. For example, these quasiparticles usually carry an electric charge, and then you can sort of imagine that with a bunch of gates on your two dimensions, you can sort of move them just the way you move electrons in wires. You can potentially move these around some imitation of a wire and then move them, or you can have like a tip of an STM, for example, and then drag these charges around in your system however you want. So you can definitely move them around, and to some extent some of this moving has actually happened. Braiding is just basically the picture you get when you're imagining time as the third dimension. Is that satisfying? Is there another question there?
Great, thank you. You answered the question.
Okay. All right. So in 2 + 1 dimensions, then two exchanges are not equivalent to identity. And you should sort of contrast this with what happens in tree space-time. Unfortunately, I don't have a picture for that, but you can sort of take this from me, that if you actually, so instead of two space dimensions here, if you actually had three-dimensional space, and then you had time as the fourth dimension, then you can show that the picture on the left and the picture on the right are actually the same thing. So sigma squared in 3 + 1 dimensions is always equal to 1. So the only thing that matters is just where the particles start and where they end. This sort of pattern of braiding actually doesn't matter in this state they are. But when we restrict our space to 2 dimensions, then there are these other possibilities. So for example, if I basically start with, just imagine I start with some initial state and I move the first particle around the second particle, and I end up with some final state that is related to initial state with some sigma, then as I just mentioned, in 3 + 1 dimensions, the sigma squared is equal to 1. And a consequence of that is that, we have identical particles that we have in nature in 3 dimensions, 3 space dimensions, are basically only bosons and fermions. And you can sort of relate this to this fact that this sigma squared in 3 + 1 dimensions is always equal to 1. So sigma can be either +1 or -1. Therefore, we have either bosons or fermions. But if we restrict ourselves to this 2 + 2 space dimensions, then interestingly, we have more possibilities. So for example, this sigma can be a phase. It can be almost any phase. It actually not exactly any phase. That the phase should be a rational fraction of pi, but still there are sort of many possibilities, and it's almost any. So the word anion, which is sort of the name of these quasiparticles, actually come from the fact that they can be, they could in principle be almost any phase when you sort of exchange two of them. So in this sort of reduced physical space, you can basically have fractional statistics. So for example, again, in the case of that I showed previously, when the filling fraction is 1/3, this space can be pi/3. Is there a question?
Yes, there is.
Mm-hmm.
So there was a question. Can you clarify if sigma is an operator?
Sigma is an operator, yes. Yeah, I mean, in a sense, you can see that, this one, or this e to the I phi is basically a scalar representation of it. So it's in this case, it's just a scalar, but as I go to the next slide, you will see that the sigma can also have a sort of matrix representation as well. So it is an operator. Okay. All right. Yeah. Okay. So you can basically sort of say that, when you sort of exchange different particles from each other, they the phases that you get form a representation of the corresponding braid group, and in this case, these are all the scalar values, so it's an Abelian representation of the braid group. Now, sort of the more exotic version, which we basically touched on briefly, these non-Abelian anyons, they have this property that, as we mentioned before, if you have a number of them present in some surface with even with trivial topology, then the corresponding Hilbert space is degenerate. So in this case, imagine that this, if I have these three anyons present, then the initial state is two-dimensional. So say psi 0 and psi 1 are my basis states. So just this psi I could be basically a superposition of these orthogonal basis states. Now, if I exchange the first one and the second one, I end up with a final state, new coefficients, again, of the same basis states. Now, if I rewrite these states in this sort of vector form, you can see that the initial state is related to the final state with a matrix. So when I actually have this degenerate Hilbert space, I can no longer represent this braiding operator with just a scalar. I need a matrix to represent that. And So this unitary matrix basically represents this topological braid operation. And because in principle, so you can imagine that, if you exchange the first two particles, you get one matrix, and if you exchange the second two particles, you get another matrix. And because in principle matrices do not commute with each other, this these sort of these operators are said to form a non-Abelian representation of the braid group, and then these anyons are said to obey non-Abelian statistics. Okay. So how is this all related to quantum computing? You can imagine that, if if you have two anyons or three anyons, and then you exchange two of them, you need basically at least a 2x2 matrix to describe that process. Now imagine if you have many of these anyons present, then depending on the dimensionality of the Hilbert space, you need a sort of a larger matrix to represent its whatever unitary operation that corresponds to braiding these particles around each other, whatever pattern that you choose. One thing that you can remember about quantum computing is, so you can sort of always think of quantum computing as whatever algorithm that you have, you can always sort of think of it as the whole thing as just basically as one big unitary operation that is acting on the space of qubits, your initial qubits. So yeah, it's true that we basically break that big unitary matrix into gates to be able to sort of apply it to individual qubits. But if you basically zoom out and look at the whole process, you can always think that you start with a bunch of initialized qubits, and then you have this big unitary operation that corresponds to your whole quantum computing. You apply that to your initial state, and you end up with a final state where you carry out your measurements. So now you can imagine that if that unitary operation that corresponds to your quantum computing can be carried out with these braids, then so in that sense, this psi initial will be the state of your initial qubit, psi final will be the state that you basically want to apply measurement to at the end of your computation, and then this matrix corresponds to all of your quantum computation. One nice property of these anyons is that if you actually have noise in the system, if these particles basically when you're moving them around each other, they're they wiggle around instead of going in a sort of a nice smooth path around each other. So long as the topology of this braid remains the same, the corresponding unitary matrix is not going to change. So you can interpret this picture as, if there are basically local noise in the system, as long as these, you can sort of think of this as the idea of, imperfect implementation of the gates due to interactions, due to random noise in the system, then as long as that noise is small enough that the shape of these braids or the topology of these braids doesn't change, then the corresponding gate is not going to change, and therefore you get your unitary matrix back. So this basically tells you that if you were able to write your gates in terms of these braids, encode your qubits using these anyons, and then carry out your gates in terms of these braids, then the computation that you carry out is going to be protected based on the properties of these anyons. So you would be able to sort of carry out the robust and scalable quantum computation this way in principle. Okay. Okay, so with this sort of rather long introduction, I can now tell you what I meant by topological quantum compiling. So imagine you have a quantum computer, and you're basically given an algorithm to just do some quantum computation, and you also have a topological quantum computer ready. The question is that how do you convert these gates to the language of braids, which is basically, you can think of as a machine language for this topological quantum computer. So that's basically the idea of compiling. You want to compile this, human understandable algorithm to this machine understandable pattern of braids. How do we do that? Again, to do quantum computing with this machine, we need to be able to encode qubits into some certain properties of these anyons, and then be able to initialize that. Then we need to carry out single qubit gates and 2 qubit gates, and finally we need to be able to measure the actual state of these qubits by, again, measuring certain properties of these anyons. So in this talk, I'm just going to focus on these two possibilities mainly, but I'll also sort of touch a little bit on these and the initialization, and definitely define encoding qubits as well. All right. Yeah, just before getting into the properties of these states, I'll say a few words about actual physical implementations of these systems. So the closest to what we think is a non-Abelian topological state is a certain fraction of quantum Hall state known as the Mourad-Pfaffian state that actually takes place at at filling fraction 5/2. So this is data from an actual experiment from back in 2004. This is the magnetic field in the horizontal line, and this is the sort of a kind of resistance that is, yeah, it's yeah, I actually, yeah, I sort of, the actual name of this resistance is actually escaping me, but it's basically in your sort of two-dimensional gas of electrons, you apply electric field. So you basically apply the magnetic field perpendicular, and then you apply some electric field to actually have some sort of a current along the sort of the length of this slab, and then you measure the voltage on the sort of on the width of this slab, and sort of the ratio of that V on the width, and then the charge on sort of the current in the perpendicular direction basically gives you this this resistant value. And anyway, sort of the idea is that I don't really want to get into too much of the details of this, how this is measured, but when you sort of plot this resistance versus the magnetic field, they're going to be, instead of having a just a sort of a constant slope as you do in the classical Hall effect, you're going to have these plateaus along the way. And that's basically where your system actually is showing an incompressible, it's basically becoming an incompressible quantum fluid. So is there a question? I see there's another.
Sorry, I couldn't hit the chat.
Yeah, Hall resistance. Yes, that is the Hall resistance. Thank you. All right, cool. Okay, so again, so I guess the idea is that, wherever you see these plateaus in the system, there is basically, that's where one of these incompressible quantum fluids are actually forming. And then you can see that the plateau at 5.5 is fairly robust, it's fairly big, and that corresponds to this Moritz-Pfaffian state. And people have shown that its excitations are these Majorana particles, which you probably have heard about in other contexts as well. They are basically, these are not, not the simplest non-Abelian anyons, but unfortunately they are, their sort of non-Abelian properties are such that they are not sufficiently rich to carry out universal quantum computing. And I actually have a bunch of slides that will show you sort of pictorially why it is that these are not good enough. Sorry, I think somebody has their, do you mind muting yourselves? Because I actually hear a lot of noise on the other side. Okay. Okay, but then there is another plateau at another filling fraction, 12/5. And you can see that it's actually sort of, it's here, and you can see it's a lot, smaller compared to 5.5. It's a lot less robust than that. And it's known as, well, it has a sort of a long name, the K3 parafermion state. And the excitations of this this state are known as Fibonacci anyons. And the good thing about them is that they're basically universal for topological quantum computation. And I will sort of give an example specifically of how to do 2-qubit gates using these Fibonacci anyons later on, hopefully, if I have time. All right. Okay, and I also sort of wanted to say very briefly that these Majorana anyons and Fibonacci anyons are two examples of anyons, of anyon models that have some experimental evidence. We have some experimental evidence for them, but in fact, there are the sort of the mathematical theory that is behind them predicts a whole sort of series of states that are known as these SU2 level K anyons. And they basically predict the presence of these, the topological phases at these particular filling fractions. And other than the fractional quantum Hollow states, people have come up with sort of very different ideas of how to implement them, though none of them have actually, other than the fractional quantum Hollow state, none of them actually have been satisfactorily, observed experimentally yet. For example, people have proposed how to create bosonic versions of these states using neutral atoms, cold, ultra cold neutral atoms, or how to, or they're basically sort of really nice model Hamiltonians for implementing these states or cousins of these states that are very closely related to these with spins, basically, and so there are spin Hamiltonians for them, and also there have been proposals of how to create them using, heterostructures of superconducting qubits, superconductors and abelian fractional quantum Hall states. So there are all these, the whole zoo of ideas of how to create these states, but they're very interesting, obviously, but they're also have proven to be very difficult to actually experimentally realize. All right, so any questions so far? Just basically, I want to get into the properties of these states and how we can actually do quantum computing with them. I guess
there is nothing in the chat right now.
Okay, very good. Okay, so so these anyons have this basically this quantum attribute, which we call topological charge. You can sort of think of it as sort of yet another quantum number similar to electric charge or spin. And in this model, the value of this topological charge is basically goes on values of 1/2. So it's kind of similar to spin. It's basically the lowest possible topological charge is 0, and that's when a state basically is vacuum as far as topological charge is concerned. The minimum value is 1/2. So whenever I'm showing you a dot, a colored dot in this talk, that corresponds to a particle with topological charge 1. And then the maximum value, it is different from a spin in the sense that there's a maximum value of what the topological charge of a sort of a bunch of anyons can be, and that's basically curbed by this integer that is basically shows in the definition of these anyons. But again, we don't need to get into too much details of the sort of the mathematics of these things, so I'm not going to sort of say much about this structure other than the properties of these topological charges, unless you want to know more. So similar to rules for adding spin, there are rules for adding topological charge. In particular, the fusion rule, which basically means if we bring two of these topological charges together, what happens to the topological? What is the topological charge of the combined object? The rule is actually very similar to the triangle rule for adding spin. You can, if you have two topological charges S1 and S2, then the minimum value of charge is the difference between them, and the maximum value is basically defined this way. Again, the maximum value is a bit different from how we define it for a spin. But for example, if you have basically two minimal charges, 1/2 and 1/2, then they can combine into an object with total topological charge 0, or an object with total topological charge 1. So in this talk, whenever I'm showing you, an oval, sort of a number of these particles enclosed by an oval, and I write a number next to it, it just basically means that if I bring these two particles close to each other, they can fuse to the sort of the topological charge as written next to this oval. Is there other questions?
Yes, it came up. We've got a couple coming through. Okay. You might have mentioned this, but why is the charge called topological?
Yeah, this is sort of a good question. And this is not the only name for this this quantity. Yeah, another I guess depending on the context it comes from, people have given it different names. Q-deformed spin is another name for this this quantity. I guess I am sort of sticking with topological charge because yeah, I mean it's sort of a charge that is defined in these topological phases, but it's not really a very good answer. So it's just basically I'm picking one of the names that are out there. Yeah, I can't really say much more than that.
Okay, so preference.
Yeah.
Okay, and the second one is, can you also speak to the experimental ways this is implemented?
Yeah, so the experiment again is so far is only this quantum Hall effect that I basically mentioned. This, that the graph that I showed you a little bit earlier. This, plotting the Hall resistance versus the magnetic field. That's the only actual experimental observation of these states so far. Again, I sort of mentioned these proposals for it that are out there, doing it with neutral atoms or doing it with spin Hamiltonians or heterostructures of superconducting qubits, superconductors and abelian Hall effect, but none of them, as far as I know, have actually been observed yet.
Okay, and then the last question. Oh, yep, thank you.
Okay.
Does it follow the law of conservation of charge?
Well, not exactly, right? Because yeah, I mean, it's kind of like spin rather than charge in that sense. If you have like two charge one halves, they can basically, in a sense, that you get two options. They can completely annihilate each other. So you just basically get zero topological charge, or they can end up with a object with total topological charge 1. So so in that sense, it's basically, as far as these representatives of topological charge is concerned, this is not conserved. You can basically have both of these outcomes.
Okay, that's it.
All right. Okay. All right. So so yeah. So I guess, I mean, again, so the interpretation of this description is that two topological charge one halves can either again give you an object with total topological charge 0, total topological charge 1. So this yeah, I guess in the interest of time I need to sort of speed up a little bit, so I guess I just remind you that you can basically, the dimensionality of the Hilbert space can be defined based on the possibilities for these fusion channels, the outcomes of these fusions. So if I have two anyons, then they can fuse into 0 or 1. So the corresponding Hilbert space is two-dimensional. If I have three, then you can basically convince yourself that if total topological charge 3/2 is a possibility, then you have basically three options. You can either get 0 from the first two and then add another one and get 1/2, or get 1 from the first two. In that case, 1 and then 1/2 can either give you 1/2 or can give you 3/2. So you have basically three options, and the corresponding space is two-dimensional. And then you can basically, it actually has been shown that depending on the theory, when you add the number of particles to your system, the dimensionality of the Hilbert space always grows exponentially. But the rate of change of Hilbert space as you add particles to your system, which is also known as quantum dimension, differs between different theories. And so, for example, you might know that if for abelian theories, obviously, no matter how many particles you add to the system, as long as the surface is just trivial, then the Hilbert space remains non-trivial. Sorry, the Hilbert space remains non-degenerate. So the rate of change of Hilbert space is 1. Whereas for Majorana particles, you might know that the rate of change of Hilbert space is square root of 2. And likewise for Fibonacci anyons, if you keep adding anyons to your system, then the dimensionality of the Hilbert space grows as Fibonacci numbers. Therefore, asymptotically, the quantum dimension is basically the golden mean. Yeah, so, but it's been sort of worked out. And just it's sort of interesting to sort of also know that these models are closely related to basically SU2 particles. So for regular electrons, just spin 1/2 particles, that corresponds to the case where k goes to infinity, and then this the quantum dimension is 2, which basically tells you that if you sort of add h particles to your system, you basically add add to the number of degrees of freedom by 2, and so the quantum dimension is 2. But anyway, it's been shown that these SU2 level k anyons are universal for quantum computing, except for k is equal to 3 or k is more than 4. So to just basically show you that, yeah, so I'll get into, I may or may not get to show you that, but I'll sort of let me just do a sort of define qubits. I guess this, just by knowing how the fusion works, we should be able to sort of define qubits. So in this representation, I use, so you need at least 3 anyons to define a qubit. Here I'm using a version that uses 4. So the qubit is basically, qubit in the state 0 is defined by 4 anyons, where the first 2 and the second 2 both fuse to 0, and then total topological charge is 0. And for the case of 1, logical 1, the first 2 and the second 2, both of them have to fuse to 1, but the total charge remains 0. So that's how we basically define the logical qubits based on these fusion possibilities of anyons. Now, if you actually work out the possibilities for the actual values of the total topological charge when you have 4 anyons, you can see that you have a maximum of 6 states. So 4 extra states other than the 2 logical qubit states. And they all correspond to having this total topological charge other than 0. They can be 1 or they can be 2. So these are basically the non-computational states. So if you define your qubits using collections of 4 anyons, and when you do computation, you should basically be careful to stay in the computational space, meaning the space of these 2 logical qubits when you're doing your work. And so any transitions between this qubit space and the non-computational space is called a leakage error. And that's something you have to be careful not to let happen. Otherwise, you corrupt your computation. All right, so far, I guess, I told you how to define qubits if you want to do this compiling. So the braids, so how do we actually do that? How do we actually do the gates? So these are, so the braid matrices for these anyon models have worked out extensively. So if within the space of a qubit, if I exchange the first 2 anyons, I get a matrix that is shown by this. The details don't matter for the purpose of this talk. And within the same basis, if you exchange the second 2 particles, then you end up with another unitary matrix. And it turns out that in this definition, the first 2 and the second 2 are completely symmetric. So sigma 3 is basically the same thing as sigma 1. So we can ignore it for the purposes of this talk. So so now if you're basically given any braid like this, you can just break it apart into these elementary braid matrices, sigma 1, sigma 2, and their inverses, read off what they are, multiply them by each other, and then the result basically become the unitary operation that corresponds to this braid. Okay, so how is this? So just back to the question of why is it that certain anyon models are universal and some of them are not? Let me just remind you that any rotation, any single qubit rotation basically can be represented by a point in a solid sphere of radius 2 pi. So your unitary operation, which can be represented as this, can be basically corresponds to sort of a dot, where sort of the length of this vector corresponds to the angle of rotation, and the direction of this vector corresponds to the direction of your rotation. So for example, a pi rotation around the x-axis will be here, or a 2 pi rotation around the y-axis will be here. And likewise, you can basically fill all of this sphere corresponding to all the elements of SU2. Now, the braid matrices for one particular theory correspond to, I'm just basically showing here for representation purposes, correspond to these 4 dots. Here I'm showing you, as you see, one particle going one complete round another one instead of just exchanging the 2 particles. This is just for just some technical reasons. There's no fundamental reason to that. So so you can see that for this particular theory, these 4 dots correspond to these 4 rotations, 4 elementary rotations, sigma 1, sigma 2, and their inverses and or their squares. Okay, now. So just to make a comparison between different anion models, for example, in particular, Majorana and Fibonacci, we know that Majorana is not universal, but Fibonacci is. Let's just see what happens if we keep adding to the length of this braid. So we just basically multiply more of these braid matrices by each other, or just basically consider all the possibilities of matrices that we get if we sort of add to the length of the braid. So here you can see that for braids of length 1, I have 4 dots in each of these spheres. Now, if I keep adding to the length of the braid, I have more and more possibilities. And you can see that for the theories that are universal, for example, the Fibonacci or k = 5, this sphere fills up pretty quickly. Whereas for Majorana and k = 4, which is also non-universal, the number of dots basically stops at some point. They start repeating each other after a certain length. So this basically shows you that with Majoranas, for example, no matter how long the length of the braid is, there's always a sort of big chunk of the sphere that you can never fill. It's just there are those unitary operations that you can never carry out. Whereas for Fibonacci, there's always so if you're willing to add to the length of the braid, you can basically just get as close as you want to sort of any unitary operation that is your target. So that's why you can actually do all single qubit gates with these guys. So therefore they are universal, whereas for these guys you cannot do all single qubit gates, therefore they're not universal. Okay. All right. So how do we carry out single qubit gates? That's actually, with this information, is fairly easy. If you're given a target gate, for example, a Hadamard gate, then all we need to do is to just basically go ahead and find a sequence of braids that best approximates this Hadamard gate. So for example, here you can actually see a sequence of about like 50 interchanges, I think it is, that corresponds to Hadamard gate to an accuracy of 10 to the -6. So it's fairly good. And it's fairly easy to do this with brute force, because you're only working with 2x2 matrices. But if you need more accuracy, you can always use the Solvay-Kitaev algorithm, or there have been actually other more efficient algorithms that have been worked out in recent years. So and also there's one really nice thing about these single qubit gates in general, and that is as long as you're braiding within an oval, you're exchanging particles within this space, the total charge of this space does not change. So in single qubit gates, you basically never have to worry about leakage errors. You always stay within this space of the qubit. So I see, is there a question?
No, I was just putting the link to the recording and everything on there. And we actually have about 1 or 2 minutes left.
Right. Okay, so this is how we do single qubit gates. The work that I actually want to really get into was the 2 qubit gates. It may take about 5 minutes. I don't know if we should do that or not.
Yeah, it's up to you, Layla. If we go a few minutes over, that should be fine. We're at 1 o'clock now.
Okay. So I'll try to finish this very quickly. So 2 qubit gates are actually hard to carry out because, first of all, in order to entangle the two qubits, you need to pull some particles from one qubit and then braid them around particles from the other qubit. And that inevitably leads to leakage errors because you can't really control the total charge of these individual qubits during this computation in general. And also, brute force search is going to be a lot more difficult because instead of having 2x2 matrices, you have, in this case, I think 14x14 matrices. So the corresponding search space is, 195 dimensional as opposed to 3 dimensions in the case of SU2. So these are very hard to carry out with brute force or even with Solvay-Kitaev. So the strategy to basically carry out these gates is to sort of somehow map this hard problem of 2-qubit gates into the easy problem of single qubit gates and then attack it that way. So how do we do this? So in this, so one of the constructions that we worked out, we focus on controlled 2-qubit gates. So which means we have these we have a control qubit and a target qubit, and then the goal is to construct a gate that affects the target qubit only when the control qubit is in the state 1 and basically do nothing otherwise. So for example, if I have a controlled phase gate like this, if the control qubit, which is represented by A, is 0, which is this first block, I get the identity. But if A is 1, which is this block, then a phase phi is applied to the target qubit when the target qubit is in the state 1, 2. So how do we actually sort of carry this out? With these braids. So the key idea here is that we basically pick a pair of particles from the control qubit and then weave that around particles in the target qubit instead of just doing, letting all the particles braid around each other. We just basically take a pair and weave that around particles in the target qubit, something like this. And the nice thing about this construction is that when this control qubit is in the state 0, which is when we're in this block of the matrix, this object with total charge 0 basically acts, as far as topological charge degree of freedom is concerned, basically acts like vacuum. So it's basically like we don't have it. So when the control qubit is in state 0, we just basically, it's just like we're not doing nothing. So we get an identity, exact identity in the first block of this matrix. Now, for the case of Fibonacci anyons, you can see that just by using this simple trick, we've already constructed controlled something gate. Now we just need to sort of work out what is in this block of the matrix. So we basically extend this trick to the target qubit as well and say now we actually sort of braid this pair of particles from the control qubit around pairs of particles in the target qubit. And if we do this, then again, we play the same game and now say, now if the target is in the state 0, we can just ignore these green lines. And then again, this is like we're just weaving the particles around nothing. So this is equivalent to just basically leaving the control anyons where they are as well. So again, when the target qubit is in the state 0, here I get an exact identity. So because it's just like I'm doing nothing. And now, so I'm basically only left. So the only with this case, which is the only non-trivial case where both control and target are in state 1. The sort of the nice thing about Fibonacci anyons is that it just happens that a pair of particles with total topological charge 1 has the same braiding properties as a single particle with charge 1/2. But in the case where both A and B are equal to 1, I can just replace them with just a single anyon. And now you can see that this looks like a single qubit all of a sudden. Now I need to find a braiding pattern that gives me the right phase right here. And that's easy to do because we know how to do single qubit gates easily. And it just turns out that for this control phase gate, control Z gate, we find a braiding pattern that corresponds to negative identity in this basis. And that's easy to carry out. And now if we follow this braiding pattern that we found via pairs of particles going around pairs of particles in the target qubit, then we end up with this matrix, which is a controlled Z. And again, the nice thing about this construction is that this is the only element in this matrix that is an approximation. Everything else is exact. Okay, so I guess I'll stop here because I don't really have time to go to the rest, and I just basically end up with a summary. Yeah. So, in this sort of pattern that we had, this, we just replace our algorithm. I sort of basically told you how to encode qubits, how to carry out single qubit gates just by carrying out the simple brute force search, and then how to carry out 2-qubit gates using this trick that I mentioned to you. And that's basically enough to do universal quantum computing, or just basically convert any algorithm that you have to a bunch of braids. So with that, I'll stop here and take any more questions that may have. Thanks for your attention.
Okay, any final questions or thoughts for Layla? Okay, I think we're good. Layla, thank you so much. I really appreciate you taking your time, and thank you to the audience for some really good questions. Appreciate it.
Thank you.
All right, everybody, we will see you back in February, on February 6th, where we'll have our talk. And you are a very good speaker. Thank you for such a clear and great presentation. You're getting a lot of shout outs. So thank you, everybody.
Thank you.